Welcome everyone to Lecture 2E, the fifth installment of Lecture 2. So this is going to be about moles and molar mass, two very important qualities or quantities when we start getting into the quantitative aspect of chemistry. So this starts the content in Chapter 3, in case you're following along in the book. And so we want to talk about what moles are, probably one of the most important units we have in chemistry. And what moles really do is it gives us a way of counting large numbers of items so that we have smaller numbers to use. So we use moles in the same way that bakers use dozens. So we know that if we go to a bakery and we ask for 12 donuts, we're going to get a dozen donuts. Or if we ask for a dozen donuts, we're going to get 12 donuts. So rather than have to ask for 12 donuts, 12 is a much bigger number than one, we can just ask for 1 dozen donuts. And so that's really all a mole is as far as numbers. So if we wanted a mole of donuts, that would be 6.022 times 10 to the 23 donuts. And that number is also very iconical. That is called Avogadro's number. He didn't discover the number, Amadeo Avogadro. He didn't discover the number, but it is named in his honor because a lot of the research he did laid the foundations for the research that did finally calculate that number. Now, it's a very large number. It's not like somebody sat around and counted out that number of atoms or molecules. That would not be possible, but there are certain ways that you can do some experimental, you can get some experimental data to find that number. But the definition that we have nowadays is that the Avogadro's number, 6.022 times 10 to the 23rd, is equal to the number of carbon-12 atoms present in 12 grams of the isotope carbon-12, which isn't very practical, but that's the definition. So the value of Avogadro's number itself isn't particularly practical unless you are dealing with very tiny numbers of particles, and then you can think about how to use that. But let's talk about that number, because when you just see a number with an exponent, it's hard really to just get how big it really is. So let's look at if we had a mole of certain things, what would that really mean? So let's say we had a mole of M&Ms. They're not a very big candy. They're just little tiny guys, about 1 centimeter in diameter. Well, I had my students once calculate how much space a mole of M&Ms would take up. And this was when I was teaching in the United States. And so a mole of M&Ms, I had them guess if it would take up, the area of our state. And we had a big state, a fairly big state. So would a mole of M&Ms cover our state? Would it cover half the United States, or would it cover the entire United States? And so most of them kind of went in between. They thought, well, it's probably just going to cover half the United States. And the actual answer is quite frightening. Not only does a mole of M&Ms cover the entire United States, it covers the entire United States to a depth of about 65 kilometers. That is insane. That is a lot of M&Ms. What if we had our mole of donuts? What if we went to our baker and asked for a mole of donuts? Well, it turns out a mole of donuts can cover the entire Earth, oceans included, and it can cover them to a depth of 8 kilometers. That's a lot of donuts. I don't think I could jog enough to work off that many donuts. What if we had a mole of basketballs? Turns out a mole of basketballs could create an entirely new planet Earth. It would take up that much space. And then my favorite, what if we had a mole of euros? Who wants to be a millionaire? Wow, that would be a lot of money. Let's say you were born with a mole of euros. If you spent 1 billion euros every second of your life and you lived to be 80 years old, at the end of those 80 years, you would have 99.999% of your money left over, spending $1 billion every single second that you were alive. That means 100,000 generations of your kin could spend $1 billion every second of their 80-year lives. That is an insane amount of money. That number of a mole is really huge. Now imagine if you just have a small cup of water. Small cup of water is about 50 to 60 milliliters. That's roughly 3 moles of molecules of water. That gives you an idea of how large the number of that a mole is, Avogadro's number is, but also gives you an idea of how small molecules really are. So kind of a fun exploration of the value of a mole. Now, again, we don't use Avogadro's number very often in terms of expressing how many molecules do we have. Instead, what we use is we talk about the number of moles. But if you've ever used a balance in lab, you know that when you go to measure something, you don't really count how many things are in there. The balance doesn't tell you how many things are in your cup. Instead, it gives you a mass. Now, when we start to work on reactions, what we also find is that we write our reaction in terms of numbers of molecules reacting. So again, we're back to numbers. So we don't have a way of turning a mass into numbers of molecules or numbers of moles. So when we write a balanced reaction, and we'll talk about those in the next lecture, or one of the next parts of lecture 2, when we start thinking about a balanced reaction, the numbers that we put in front of our chemical formulas, we can think of either in terms of numbers of molecules, but we can also think of them in terms of numbers of moles. And the reason for that is that an element's mass of 1 mole of material in grams is equal numerically to 1 atom's mass of that element in AMUs. So if we look at carbon, we see that 12.011 under the symbol for carbon, under that C. And that means that 1 atom of carbon on average weighs 12.011 AMUs. But it also means that Avogadro's number, or 1 mole of carbon atoms, is going to weigh 12.011 grams. And this gives us a very nice way of converting between the number of moles, which represents a number of particles that we write our reactions in terms of, and mass, which is something that we can weigh out on one of our devices. So we get this information from the periodic table, and molar mass actually becomes a conversion factor because it gives us the number of grams per mole. Okay, grams per mole. Anytime you have 2 units, one over the other, that becomes a conversion factor because we know the number of grams per moles. So this becomes a conversion factor between mass and the number of moles. So take a look at copper, take a look at aluminum, and you'll see that those have different values for their atomic mass because the atoms are different sizes. And so when you have a mole of aluminum atoms, it weighs a certain amount, and when you have a mole of copper atoms, it weighs a different amount. Even though you have the same number of particles, those particles are different. It's just like a dozen grapes would weigh different from a dozen watermelons. Okay, so how do we use our molar mass? Here's an example that I will work out and put in a link for YouTube, and you can watch that. And here's another example going the other way. So the first one we are converting grams into moles, and this one we're going to convert moles into grams. And again, look for this link. So we've talked about molar mass of an element, a compound, something we find directly on the periodic table, but most of the chemistry that we do does not involve just an atom. It involves molecules, compounds. And so how do we find the molar mass of a compound? So we express molar mass in the exact same way, grams per mole, and it turns out that the numerical values of these are identical and equal to the sum of all of the atomic masses in the compound. Okay, so what we do is we take the formula mass, or to find the formula mass, that's the same thing as the molar mass. We find the number of atoms of the first element listed in the compound, and we multiply that by the atomic mass from the periodic table for that element. And then we take the second one, and we do the same thing. We add those numbers together, and we do the same thing for the third element until you've run out of elements for the compound. So let's say that we have ammonia, NH3, a nice small molecule. So in our formula for ammonia, NH3, we have 1N. So in a mole of NH3, we would have 1 mole of nitrogen atoms. And so 1 mole of nitrogen atom weighs 14.007 grams per 1 mole. Okay, and when we multiply, we can always use some unit analysis here, so we can cancel our moles of N there when we multiply through, and we're left with only grams. Now for our hydrogen, we see that we have 3 hydrogens for every NH3 molecule. That means for every mole of NH3, I'm going to have 3 moles of hydrogens. Each mole of hydrogen atoms weighs 1.008 grams. And again, that comes directly from the periodic table, so that's per 1 mole of H. And so now my moles of H cancel out, and I'm just left with grams. So I have 1 times 14.007 plus 3 times 1.008, and I get this answer here, 17.031 grams. So that would be the number of grams in 1 mole of ammonia. So grams per 1 mole. Here's an example I'd like you to try. This involves pyridine. It's a clear liquid. It's very common in organic chemistry laboratories. It is a very foul-smelling chemical. I find it. It's kind of a sugary, sweet, fishy smell. It's just nasty. But it is a very useful molecule. It has a chemical formula of C5H5N. So it has 5 carbon atoms, 5 hydrogen atoms, and 1 nitrogen atom in each of its molecules. And using the periodic table information below, you should be able to find its molar mass. And again, look for a link on how to calculate that.